Methods in Biological Studies 1. Biophysical methods. Biophysical methods are instrumental in elucidating the structural and functional dynamics of biological molecules and systems. By applying principles from physics, these techniques provide insights into molecular structures, interactions, and behaviors that are fundamental to understanding complex biological processes. 1. Spectroscopy. Spectroscopic techniques analyze the interaction between electromagnetic radiation and matter, offering detailed information about molecular structures and dynamics. Nuclear magnetic resonance (NMR) spectroscopy. NMR exploits the magnetic properties of certain atomic nuclei to determine the physical and chemical properties of atoms or molecules. It's pivotal in elucidating the three-dimensional structures of proteins and nucleic acids in solution, providing insights into molecular conformations and dynamics. Mass spectrometry (MS). MS measures the mass-to-charge ratio of ions to identify and quantify molecules, especially proteins and metabolites. It's essential for proteomics and metabolomics studies, enabling the analysis of complex biological mixtures with high sensitivity. Circular dichroism (CD) spectroscopy. CD measures the differential absorption of left and right circularly polarized light, offering information about the secondary structures of proteins and nucleic acids. It's particularly useful for assessing protein folding and conformational changes. 2. Microscopy and imaging. Advanced imaging techniques allow for the visualization of biological structures at various scales, from tissues to individual molecules. Electron microscopy (EM). EM uses electron beams to achieve high-resolution images of biological specimens. Transmission electron microscopy (TEM) provides detailed internal structures, while scanning electron microscopy (SEM) offers surface topology. Atomic force microscopy (AFM). AFM employs a cantilever with a sharp tip to scan the specimen's surface, generating topographical maps at the nanoscale. It's invaluable for studying the mechanical properties of biomolecules and cells. Fluorescence microscopy. This technique utilizes fluorescent probes to label specific cellular components, enabling the observation of dynamic processes in live cells. Confocal microscopy enhances image resolution by eliminating out-of-focus light. 3. Calorimetry. Calorimetric methods measure the heat changes associated with biochemical reactions, providing insights into binding interactions and thermodynamics. Isothermal titration calorimetry (ITC). ITC quantifies the heat released or absorbed during molecular interactions, allowing for the determination of binding constants, stoichiometry, enthalpy, and entropy changes. Differential scanning calorimetry (DSC). DSC measures heat capacity changes as a function of temperature, offering information about the stability and folding of macromolecules. 4. Electrophysiology. Electrophysiological techniques investigate the electrical properties of biological cells and tissues. Batch clamp technique. This method records ionic currents through individual ion channels and membranes, providing insights into their functional properties and regulation. Electroencephalography (EEG) measures electrical activity in the brain, aiding in the study of neural networks and brain function. 5. Hydrodynamic methods. These techniques analyze the behavior of molecules in solution under the influence of external forces. Analytical ultracentrifugation (AUC). AUC separates molecules based on their size, shape, and density, allowing for the determination of molecular weights and interaction parameters. Dynamic light scattering (DLS). DLS measures fluctuations in light scattering due to particle motion, providing information on the size distribution of macromolecules and complexes in solution. 6. Surface plasmon resonance (SPR). SPR detects changes in the refractive index near a sensor surface, enabling real-time monitoring of biomolecular interactions without labeling. It's widely used to study kinetics and affinities of ligand receptor bindings. 7. Single molecule techniques. These methods allow for the observation and manipulation of individual molecules, offering insights into heterogeneity and dynamic processes. Optical tweezers. Utilizing focused laser beams, optical tweezers can trap and manipulate single molecules, facilitating the study of molecular motors and force measurements. Fluorescence resonance energy transfer. FRET measures energy transfer between two fluorophores in close proximity, providing information on molecular distances and conformational changes. Incorporating these biophysical methods into biological research enhances our understanding of molecular mechanisms, contributing to advancements in fields like drug discovery, structural biology, and molecular physiology. Sample question and solution. Question. Describe the principle of isothermal titration calorimetry (ITC) and its application in studying biomolecular interactions. Answer. Isothermal titration calorimetry (ITC) is a biophysical technique that measures the heat change associated with molecular interactions in solution. During an ITC experiment, one reactant is titrated into a solution containing another reactant at a constant temperature. The heat released or absorbed upon binding is detected and quantified, allowing for the determination of thermodynamic parameters such as binding affinity (K_D), enthalpy (delta_H), entropy (delta_S), and stoichiometry (N) of the interaction. ITC is widely used to study interactions between proteins, nucleic acids, lipids, and small molecules, providing comprehensive insights into the forces driving biomolecular associations. By mastering these concepts and techniques, candidates will be well prepared to tackle questions related to biophysical methods in the University of Calicut PhD entrance examination for zoology. You said. You said. Molecular analysis using UV visible fluorescence, ChatGPT said. Molecular analysis often employs spectroscopic techniques such as ultraviolet visible UV-vis spectroscopy and fluorescence spectroscopy to investigate the structural and functional properties of biomolecules. These methods provide complementary insights into molecular characteristics, enabling a comprehensive understanding of biological systems. Ultraviolet visible UV-vis spectroscopy. UV-vis spectroscopy measures the absorption of light in the ultraviolet and visible regions of the electromagnetic spectrum by a sample. The absorption pattern, or spectrum, reflects the electronic transitions within the molecules, particularly those involving pi electrons and non-bonding electrons. This technique is instrumental in determining the concentration of nucleic acids and proteins, as their aromatic residues absorb light at characteristic wavelengths. For instance, nucleic acids exhibit a peak around 260 nanometers, while proteins typically absorb near 280 nanometers. By applying the Beer-Lambert law, which relates absorbance to concentration, researchers can quantify these biomolecules with precision. Fluorescence spectroscopy. Fluorescence spectroscopy involves the measurement of light emitted by a substance after it has absorbed light or other electromagnetic radiation. Upon excitation by a specific wavelength, certain molecules emit light at a longer wavelength, a phenomenon known as fluorescence. This method is highly sensitive and is utilized to detect and quantify low-abundance biomolecules, study molecular interactions, and monitor dynamic processes within cells. Fluorescent probes and dyes can be employed to label specific cellular components, enabling real-time visualization of biological events. Complementary use of UV-vis and fluorescence spectroscopy. While UV-vis spectroscopy provides information based on the absorption characteristics of molecules, fluorescence spectroscopy offers enhanced sensitivity by detecting emitted light from fluorescent species. Combining these techniques allows for a more robust analysis. For example, UV-vis spectroscopy can determine the optimal excitation wavelength for a sample, which can then be used in fluorescence measurements to study emission properties. This integrated approach is particularly beneficial in fields like biochemistry and molecular biology, where understanding both the concentration and behavior of biomolecules is crucial. BioCompare. Com. Sample question and solution. Question. Explain the principle of fluorescence spectroscopy and discuss its applications in studying protein-ligand interactions. Answer. Fluorescence spectroscopy is based on the principle that certain molecules, upon absorbing light at a specific excitation wavelength, re-emit light at a longer emission wavelength. This emission results from the return of excited electrons to their ground state, releasing energy in the form of light. The intensity and wavelength of the emitted light provide insights into the molecular environment and dynamics. In studying protein-ligand interactions, fluorescence spectroscopy is invaluable. Intrinsic fluorescence from aromatic amino acids like tryptophan can change upon ligand binding, indicating conformational alterations. Additionally, extrinsic fluorescent probes can be attached to either the protein or ligand. Changes in their fluorescence upon interaction reveal binding events, affinities, and kinetics, thereby elucidating the molecular mechanisms governing these interactions. Multiple choice questions. Which of the following statements correctly differentiates between UV-vis and fluorescence spectroscopy? A. UV-vis spectroscopy measures light emission, while fluorescence spectroscopy measures light absorption. B. UV-vis spectroscopy is more sensitive than fluorescence spectroscopy. C. Fluorescence spectroscopy detects emitted light from a sample after excitation, whereas UV-vis spectroscopy measures the light absorbed by the sample. D. Both techniques measure the same parameters and are interchangeable. Answer. C. Fluorescence spectroscopy detects emitted light from a sample after excitation, whereas UV-vis spectroscopy measures the light absorbed by the sample. In UV-vis spectroscopy, the Beer-Lambert law relates which of the following parameters? A. Absorbance, molar extinction coefficient, path length, and concentration. B. Emission intensity, quantum yield, and concentration. C. Excitation wavelength, emission wavelength, and fluorescence lifetime. D. Absorbance, fluorescence intensity, and molecular weight. Answer. A. Absorbance, molar extinction coefficient, path length, and concentration. Which of the following applications is best suited for fluorescence spectroscopy? A. Quantifying high concentration analytes in solution. B. Determining the molecular weight of proteins. C. Investigating real-time dynamics of protein-ligand interactions. D. Measuring the refractive index of a solution. Answer. C. Investigating real-time dynamics of protein-ligand interactions. By mastering these spectroscopic techniques and their applications, candidates will be well prepared to address related questions in the University of Calicut PhD entrance examination for zoology. Sources. You said. Circular dichroism. ChatGPT said. Circular dichroism (CD) spectroscopy is a powerful analytical technique used to study the chiral properties of molecules, particularly in understanding the secondary structures of proteins and nucleic acids. By measuring the differential absorption of left and right circularly polarized light, CD provides insights into the conformational characteristics of biomolecules. Principle of circular dichroism. CD arises from the differential absorption of left-handed and right-handed circularly polarized light by chiral molecules. When such light passes through an optically active substance, the difference in absorption leads to ellipticity in the transmitted light, which is measured as a function of wavelength. This ellipticity is indicative of the molecule's chiral environment and can be used to deduce structural information. Applications of circular dichroism. Protein secondary structure analysis. CD is extensively used to determine the secondary structures of proteins, such as alpha helices, beta sheets, and random coils. Each of these structures exhibits characteristic CD spectra in the far UV region, 190-250 nanometers, allowing researchers to estimate the content and conformational changes in proteins. Chem. Libretex. Org. Nucleic acid conformation studies. CD spectroscopy aids in analyzing the conformations of nucleic acids, including distinctions between A form, B form, and Z form DNA. The technique provides information on structural transitions and interactions with ligands or proteins. Monitoring protein folding and stability. By observing changes in the CD spectrum, scientists can monitor protein folding processes and assess the stability of proteins under various conditions, such as changes in temperature, pH, or the presence of denaturants. Drug biomolecule interactions. CD is utilized to study interactions between drugs and their biomolecular targets. Binding events often induce conformational changes in the biomolecule, which are detectable through alterations in the CD spectrum. Sample question and solution. Question. How can circular dichroism spectroscopy be employed to assess the denaturation of a protein? Answer. Circular dichroism spectroscopy measures the differential absorption of circularly polarized light by chiral molecules, providing information about their secondary structures. Proteins exhibit characteristic CD spectra corresponding to their secondary structures, such as alpha helices and beta sheets. Upon denaturation, these structures unfold, leading to distinct changes in the CD spectrum. By monitoring the CD signal, particularly in the far UV region, researchers can detect alterations indicative of protein denaturation, thereby assessing structural integrity under various conditions. Multiple choice questions. Which region of the electromagnetic spectrum is primarily used in circular dichroism spectroscopy to analyze protein secondary structures? A. Near UV 250-300 nanometers. B. Far UV 190-250 nanometers. C. Visible 400-700 nanometers. D. Infrared 700-1000 nanometers. Answer. B. Far UV 190-250 nanometers. What does a characteristic CD spectrum in the far UV region indicate about a protein? A. Its tertiary structure. B. Its secondary structure. C. Its quaternary structure. D. Its primary amino acid sequence. Answer. B. Its secondary structure. In CD spectroscopy, what causes the differential absorption of left and right circularly polarized light? A. The presence of chromophores. B. The chiral nature of the molecule. C. The molecular weight of the compound. D. The solvent used. Answer: B. The chiral nature of the molecule. Understanding the principles and applications of circular dichromosome spectroscopy equips researchers with a valuable tool for probing the structural nuances of biomolecules, thereby enhancing insights into their functional roles in biological systems. Sources: You said, NMR. ChatGPT said. Nuclear magnetic resonance (NMR) spectroscopy is a powerful analytical technique used to determine the structure, dynamics, reaction state, and chemical environment of molecules. It exploits the magnetic properties of certain atomic nuclei, providing detailed information about the electronic structure of molecules and their spatial arrangement. Principle of NMR spectroscopy. NMR spectroscopy is based on the absorption of radiofrequency radiation by nuclei in a strong magnetic field. Nuclei with a non-zero spin, such as (1H and (13C), possess a magnetic moment. When placed in an external magnetic field, these nuclear spins align either with or against the field, creating distinct energy levels. The application of radiofrequency radiation induces transitions between these energy levels, and the resulting absorption is measured to produce an NMR spectrum. The resonance frequency of a nucleus is influenced by its chemical environment, allowing for the elucidation of molecular structures. Applications of NMR spectroscopy. Structural elucidation. NMR is extensively used to determine the three-dimensional structures of organic compounds, proteins, and nucleic acids. By analyzing chemical shifts, coupling constants, and signal intensities, researchers can deduce the connectivity and spatial arrangement of atoms within a molecule. Dynamic studies. NMR enables the investigation of molecular dynamics, including conformational changes, protein folding, and interactions between biomolecules. Techniques such as relaxation measurements and exchange spectroscopy provide insights into motion and kinetics at the atomic level. Quantitative analysis. The technique allows for the precise quantification of compounds in a mixture. The area under an NMR signal is directly proportional to the number of nuclei contributing to that signal, facilitating accurate concentration determinations. Medical imaging. In the form of magnetic resonance imaging, MRI, NMR principles are applied clinically to produce detailed images of soft tissues in the human body, aiding in medical diagnosis and research. Sample question and solution. Question: Explain how NMR spectroscopy can be utilized to determine the purity of a synthesized organic compound. Answer: NMR spectroscopy assesses the purity of a synthesized organic compound by analyzing its spectral data. A pure compound typically exhibits a characteristic set of NMR signals corresponding to its unique molecular structure. Impurities manifest as additional, unexpected signals in the spectrum. By comparing the observed spectrum to that of the pure reference compound, one can identify and quantify these extraneous peaks, thereby determining the presence and extent of impurities. Integration of the signal areas allows for the estimation of the relative concentrations of the compound and its impurities, providing a comprehensive assessment of purity. Multiple choice questions. Which of the following nuclei is commonly analyzed in NMR spectroscopy? A (12C), B (14N), C (16O), D (1H). Answer: D (1H). In NMR spectroscopy, the chemical shift is measured in which units? A Hertz (HC), B parts per million ppm, C Tesla T, D Gauss G. Answer: B parts per million ppm. What is the primary purpose of applying an external magnetic field in NMR spectroscopy? A to ionize the sample, B to align the nuclear spins, C to excite electrons to higher energy levels, D to induce chemical reactions. Answer: B to align the nuclear spins. A thorough understanding of NMR spectroscopy principles and applications is essential for interpreting molecular structures and dynamics, making it a vital tool in advanced biological studies. Sources: You said, ESR spectroscopy. ChatGPT said. Electron spin resonance (ESR) spectroscopy, also known as electron paramagnetic resonance (EPR) spectroscopy, is a powerful analytical technique used to study materials with unpaired electrons. It provides detailed insights into the electronic structure, dynamics, and spatial distribution of paramagnetic species, which are crucial in various fields such as chemistry, biology, and material science. Principle of ESR spectroscopy. ESR spectroscopy is based on the interaction between unpaired electron spins in an external magnetic field. When a paramagnetic sample is exposed to a constant magnetic field and irradiated with microwave radiation, transitions occur between the magnetic energy levels of the unpaired electrons. The resonance condition is met when the energy of the microwave photons matches the energy difference between these levels, resulting in the absorption of microwave energy. This absorption is detected and plotted as an ESR spectrum, which reveals information about the electronic environment and the nature of the paramagnetic species. Applications of ESR spectroscopy. Study of free radicals. ESR is extensively used to detect and characterize free radicals in chemical and biological systems. It provides information on the formation, stability, and reactions of these highly reactive species. Transition metal complexes. ESR aids in investigating the electronic structures of transition metal ions, offering insights into their oxidation states, coordination environments, and ligand interactions. Biological systems. In biochemistry, ESR is employed to study metalloproteins, enzymes, and other biomolecules containing paramagnetic centers, enhancing the understanding of their functional mechanisms. Radiation dosimetry. ESR is utilized in measuring radiation exposure by detecting radiation-induced free radicals in substances like tooth enamel and certain dosimetric materials. Material science. ESR assists in characterizing defects and impurities in semiconductors, insulators, and other materials, contributing to the development of electronic and photonic devices. Sample question and solution. Question: How can ESR spectroscopy be applied to study the active sites of metalloproteins? Answer: Metalloproteins often contain paramagnetic metal ions at their active sites. ESR spectroscopy detects the unpaired electrons associated with these metal centers, providing detailed information about their electronic environments. By analyzing the ESR spectra, researchers can deduce the geometry, oxidation state, and ligand field of the metal ions, leading to a deeper understanding of the protein's catalytic mechanisms and functions. Multiple choice questions. Which of the following species can be directly studied using ESR spectroscopy? A. Diamagnetic molecules, B. Paramagnetic ions, C. Noble gases, D. Nonpolar covalent compounds. Answer, B. Paramagnetic ions. In ESR spectroscopy, the G factor provides information about the nuclear spin of the atom. B. The electronic environment of the unpaired electron. C. The mass of the electron. D. The vibrational states of the molecule. Answer, B. The electronic environment of the unpaired electron. What is the typical frequency range of the microwave radiation used in ESR spectroscopy? A. 30 to 300 Hz. B. 30 to 300 kHz. C. 30 to 300 MHz. D. 30 to 300 GHz. Answer, D. 30 to 300 GHz. A comprehensive understanding of ESR spectroscopy equips researchers with a versatile tool for probing the characteristics of paramagnetic species, thereby advancing knowledge in various scientific disciplines. Sources. You said. Molecular structure determination using X-ray diffraction. ChatGPT said. X-ray diffraction (XRD) is a pivotal technique for elucidating the atomic and molecular structures of crystalline substances. By analyzing the patterns produced when X-rays interact with a crystal lattice, researchers can determine the precise arrangement of atoms within the material. Principle of X-ray diffraction. When a crystalline material is exposed to incident X-rays, the periodic arrangement of atoms causes the X-rays to diffract in specific directions. This diffraction occurs because the wavelength of X-rays is comparable to the interatomic distances in crystals. The relationship governing this phenomenon is described by Bragg's law. N lambda equals 2 d sin theta. N lambda equals 2 d sin theta. Here, n is an integer representing the order of the diffraction, lambda. Lambda is the wavelength of the incident X-ray beam, d. D is the distance between atomic layers in the crystal, and theta. Theta is the angle of incidence. By measuring the angles theta and intensities of the diffracted beams, one can infer the distances between planes of atoms and, consequently, the three-dimensional structure of the molecule. Applications of X-ray diffraction. Determination of molecular structures. XRD is extensively used to ascertain the structures of complex biomolecules, including proteins and nucleic acids. By analyzing the diffraction patterns, scientists can construct detailed models of molecular geometries, which are crucial for understanding biological functions and interactions. Material science. In materials research, XRD aids in identifying crystalline phases, assessing purity, and evaluating structural properties. It is instrumental in the development of new materials and the improvement of existing ones. Pharmaceuticals. XRD plays a vital role in drug development by revealing the structures of pharmaceutical compounds, thereby facilitating the design of more effective and targeted therapeutics. Sample question and solution. Question. Describe how X-ray diffraction can be utilized to determine the structure of a protein. Answer. To determine a protein's structure using X-ray diffraction, the protein must first be crystallized. Once a high-quality crystal is obtained, it is exposed to a focus beam of X-rays. As the X-rays interact with the electron clouds of the atoms in the crystal, they are diffracted, producing a pattern of spots known as reflections. This diffraction pattern is recorded and analyzed using computational methods to reconstruct the electron density map of the protein. By interpreting this map, researchers can model the precise arrangement of atoms within the protein, providing insights into its functional mechanisms. Multiple choice questions. What is the primary purpose of using X-ray diffraction in molecular biology? A. To measure the mass of molecules. B. To determine the three-dimensional structure of biomolecules. C. To analyze the thermal stability of compounds. D. To study the optical properties of materials. Answer. B. To determine the three-dimensional structure of biomolecules. In Bragg's law, the variable d represents a. The wavelength of the incident X-ray beam. B. The distance between atomic layers in a crystal. C. The angle of incidence. D. The order of diffraction. Answer. B. The distance between atomic layers in a crystal. Which of the following is a prerequisite for performing X-ray diffraction analysis on a protein? A. The protein must be in a gaseous state. B. The protein must be crystallized. C. The protein must be denatured. D. The protein must be labeled with a fluorescent tag. Answer. B. The protein must be crystallized. A comprehensive understanding of X-ray diffraction principles and applications is essential for elucidating molecular structures, thereby advancing research in various scientific disciplines. Sources. You said. Molecular structure determination using NMR. ChatGPT said. Nuclear magnetic resonance (NMR) spectroscopy is a powerful analytical technique used to determine the three-dimensional structures of molecules, particularly organic compounds and biomolecules, in solution. By analyzing the magnetic properties of certain atomic nuclei, NMR provides detailed information about the spatial arrangement of atoms within a molecule, as well as insights into molecular dynamics and interactions. Principle of NMR spectroscopy. NMR spectroscopy exploits the magnetic properties of nuclei, such as hydrogen 1-1H and carbon 13-13C, which possess intrinsic spin. When placed in a strong external magnetic field, these nuclear spins align with or against the field, creating distinct energy levels. Exposure to radio frequency radiation induces transitions between these energy levels, and the resulting absorption is detected as an NMR signal. The resonance frequency of each nucleus is influenced by its electronic environment, leading to chemical shifts that provide insights into the molecular structure. Key parameters in NMR spectroscopy. Chemical shift delta indicates the resonance frequency of a nucleus relative to a standard reference, revealing information about the electronic environment surrounding the nucleus. Spin-spin coupling J-coupling interaction between neighboring nuclear spins causes splitting of NMR signals into multiplets, providing information about the number and proximity of adjacent nuclei. Signal integration. The area under an NMR signal correlates with the number of nuclei contributing to that signal, allowing for the determination of relative quantities of different types of atoms in the molecule. Applications of NMR spectroscopy. Structural elucidation of organic compounds. NMR is instrumental in identifying and characterizing organic molecules by revealing their structural frameworks and functional groups. Protein and nucleic acid structure determination. Multidimensional NMR techniques enable the determination of high-resolution structures of proteins and nucleic acids in solution, providing insights into their functional conformations and dynamics. Studying molecular dynamics. NMR relaxation measurements offer information on molecular motions and conformational flexibility, which are crucial for understanding biological functions and interactions. Sample question and solution. Question. How does spin-spin coupling and NMR spectroscopy assist in determining the connectivity of atoms within a molecule? Answer. Spin-spin coupling, or J-coupling, arises from interactions between neighboring nuclear spins, leading to the splitting of NMR signals into multiplets. The pattern and magnitude of this splitting provide information about the number of adjacent nuclei and their connectivity. By analyzing these coupling patterns, chemists can deduce which atoms are bonded to each other, thereby elucidating the molecule's structural framework. Multiple choice questions. Which of the following nuclei is commonly analyzed in NMR spectroscopy for structural determination? A-12C. B-14N. C-1H. D-16O. Answer. C-1H. In NMR spectroscopy, the chemical shift provides information about A. The number of neighboring nuclei. B. The electronic environment surrounding a nucleus. C. The molecular weight of the compound. D. The temperature of the sample. Answer. B. The electronic environment surrounding a nucleus. What does the integration of an NMR signal represent? A. The chemical shift of the nucleus. B. The coupling constant between nuclei. C. The relative number of nuclei contributing to the signal. D. The magnetic field strength. Answer. C. The relative number of nuclei contributing to the signal. A thorough understanding of NMR spectroscopy principles and applications is essential for accurately determining molecular structures and gaining insights into molecular behavior in various chemical and biological contexts. Sources. You said. From now on, provide more elaborate and important theory lectures. ChatGPT said. Memory updated. Got it. I'll provide even more detailed and comprehensive theory lectures for your PhD entrance exam preparation. Let me know the next topic, and I'll make sure to cover it thoroughly. You said. Molecular analysis using light scattering. ChatGPT said. Light scattering techniques are indispensable tools in molecular analysis, providing critical insights into the size, shape, molecular weight, and interactions of macromolecules in solution. These non-invasive methods are pivotal in fields such as biochemistry, molecular biology, and polymer science, enabling researchers to characterize molecules without altering their native states. Principles of light scattering. When light encounters particles or macromolecules in solution, it is scattered in various directions. The intensity and pattern of this scattered light depend on factors such as the size, shape, and molecular weight of the scattering entities. By analyzing these scattering patterns, valuable information about the molecular characteristics can be obtained. Types of light scattering techniques. Static light scattering, SLS. Objective, determines the absolute molecular weight and the radius of gyration of macromolecules. Methodology, measures the time averaged intensity of scattered light at different angles. The data obtained are used to construct a Zim plot, from which molecular weight and size are derived. Applications, widely used in the characterization of polymers and proteins to assess their molecular dimensions and aggregation states. Dynamic light scattering, DLS. Objective, measures the hydrodynamic radius and assesses the size distribution of particles in solution. Methodology, analyzes the fluctuations in the intensity of scattered light over time, which result from the Brownian motion of particles. The autocorrelation function of these fluctuations provides information about the diffusion coefficients, from which particle sizes are calculated. Applications, essential for studying the size distribution of nanoparticles, colloids, and macromolecular assemblies, as well as monitoring aggregation phenomena. Key parameters in light scattering. Molecular weight, MW, represents the mass of a molecule. SLS provides an absolute measurement of MW without the need for external calibration standards. Radius of gyration, RG, indicates the root mean square distance of a molecule's mass distribution from its center of mass, offering insights into its overall shape. Hydrodynamic radius, RH, reflects the apparent size of a particle as it diffuses through a solvent, ascertained through DLS measurements. Second virial coefficient, A2, provides information about intermolecular interactions, with positive values indicating repulsion and negative values suggesting attraction between molecules. Applications of light scattering in molecular analysis. Protein characterization, determines molecular weight, oligomerization states, and aggregation behavior, which are crucial for understanding protein function and stability. Polymer science, assesses molecular weight distribution, branching, and conformation of synthetic and natural polymers, aiding in the development of materials with desired properties. Nanoparticle analysis, evaluates size distribution and stability of nanoparticles, essential for applications in drug delivery and nanotechnology. Quality control, monitors consistency and stability of biopharmaceuticals and other products by detecting aggregation or changes in molecular size. Sample question and solution. Question, explain how dynamic light scattering, DLS, can be utilized to determine the size distribution of nanoparticles in a colloidal solution. Answer, dynamic light scattering, DLS, measures the temporal fluctuations in the intensity of scattered light caused by the Brownian motion of nanoparticles in a colloidal solution. These fluctuations are analyzed to obtain the autocorrelation function, which relates to the diffusion coefficients of the particles. Using the Stokes-Einstein equation, these diffusion coefficients are converted into hydrodynamic radii, providing a size distribution profile of the nanoparticles. DLS is particularly advantageous due to its sensitivity to small particles and its ability to deliver rapid measurements without the need for extensive sample preparation. Multiple choice questions. Which light scattering technique is primarily used to determine the hydrodynamic radius of macromolecules in solution? A. Static light scattering, SLS. B. Dynamic light scattering, DLS. C. Rayleigh scattering. D. Mie scattering. Answer, B. Dynamic light scattering, DLS. In static light scattering, SLS, the Zim plot is used to determine A. Hydrodynamic radius and particle size distribution. B. Molecular weight and radius of gyration. C. Scattering intensity and angle of incidence. D. Diffusion coefficient and concentration. Answer, B. Molecular weight and radius of gyration. The second virial coefficient, A2, obtained from light scattering measurements provides information about A. Molecular shape and conformation. B. Intermolecular interactions. C. Particle velocity in solution. D. Wavelength of incident light. Answer, B. Intermolecular interactions. A comprehensive understanding of light scattering techniques and their applications is essential for accurately characterizing molecular properties, thereby advancing research and development in various scientific disciplines. Sources. You said. Different types of mass spectrometry, ChatGPT said. Mass spectrometry, MS, is a powerful analytical technique used to identify and quantify molecules by measuring their mass to charge ratios, m/z. Central to this process are mass analyzers, which separate ions based on their MZ values. Various types of mass spectrometers have been developed, each employing different mass analyzers tailored to specific analytical needs. 1. Quadrupole mass analyzer. The quadrupole mass analyzer consists of 4 parallel rods with applied direct current DC and radio frequency RF voltages. These voltages create oscillating electric fields that allow only ions of a specific MZ to pass through to the detector, while others are filtered out. Quadrupole analyzers are widely used due to their robustness, affordability, and suitability for both qualitative and quantitative analyses. 2. Time-of-flight TOF mass analyzer. In a time-of-flight analyzer, ions are accelerated by an electric field to the same kinetic energy and then allowed to drift through a field-free region. Since all ions have the same kinetic energy, their velocities, and thus the time they take to reach the detector, depend on their MZ values. TOF analyzers are known for their high mass range and rapid data acquisition, making them ideal for analyzing large biomolecules like proteins. 3. Magnetic sector mass analyzer. Magnetic sector analyzers use a magnetic field to deflect ions based on their MZ ratios. Ions are accelerated into a magnetic field, and their paths curve according to their momentum and charge. By adjusting the magnetic field strength, ions of different MZ can be focused onto the detector sequentially. These analyzers are valued for their high precision and are often employed in applications requiring exact mass measurements. 4. Electrostatic sector mass analyzer. Electrostatic sector analyzers utilize an electric field to separate ions by their kinetic energy. Ions pass through an electric field that causes them to follow curved trajectories. Only ions with specific kinetic energies and thus specific MZ ratios reach the detector. These analyzers are often combined with magnetic sectors in double focusing mass spectrometers to enhance resolution and accuracy. 5. Quadrupole ion trap mass analyzer. Quadrupole ion traps confine ions using oscillating electric fields within a three-dimensional quadrupole field. By varying the electric fields, ions of different MZ ratios can be ejected sequentially to the detector. Ion traps are versatile and capable of performing multiple stages of mass spectrometry (ms-n), making them useful for structural elucidation of complex molecules. 6. Fourier transform ion cyclotron resonance (FORT-ICR) mass analyzer. FORT-ICR analyzers trap ions in a strong magnetic field, causing them to move in circular paths at frequencies dependent on their MZ ratios. By detecting these frequencies, the MZ values of the ions can be determined with extremely high resolution and mass accuracy. FORT-ICR is particularly useful in proteomics and complex mixture analysis due to its exceptional resolving power. 7. Orbitrap mass analyzer. The orbitrap analyzer traps ions in an electrostatic field, causing them to orbit around a central spindle electrode. The frequency of this motion is related to the ions' MZ ratios. By measuring these frequencies, the orbitrap provides high resolution and accurate mass measurements. It is widely used in applications requiring precise mass determination, such as metabolomics and proteomics. Sample question and solution. Question: explain how a time-of-flight TOF mass analyzer separates ions based on their mass-to-charge ratios. Answer: in a TOF mass analyzer, ions are first accelerated by an electric field to impart them with uniform kinetic energy. These ions then enter a field-free drift region where they travel toward the detector. Since all ions possess the same kinetic energy, their velocities are inversely proportional to the square root of their masses. Consequently, ions with lower MZ ratios reach the detector more quickly than those with higher MZ ratios. By precisely measuring the time each ion takes to reach the detector, the TOF analyzer calculates their MZ values, effectively separating ions based on their mass-to-charge ratios. Multiple choice questions. Which mass analyzer utilizes oscillating electric fields to selectively stabilize or destabilize ions based on their mass-to-charge ratios? A time-of-flight TOF. B. Quadrupole. C. Magnetic sector. D. Orbitrap. Answer: B. Quadrupole. Which mass analyzer is known for providing extremely high resolution and mass accuracy by trapping ions in a strong magnetic field? A quadrupole ion trap. B. Electrostatic sector. C. Fourier transform ion cyclotron resonance (FORT-ICR). D. Time-of-flight TOF. Answer: C. Fourier transform ion cyclotron resonance (FORT-ICR). In which mass analyzer do ions orbit around a central spindle electrode, allowing for high-resolution mass measurements? A. Magnetic sector. B. Quadrupole. C. Orbitrap. D. Time-of-flight TOF. Answer: C. Orbitrap. Understanding the various types of mass spectrometers and their operating principles is crucial for selecting the appropriate instrument for specific analytical applications, thereby enhancing the accuracy and efficiency of molecular analyses. Sources: You said. Surface plasma resonance methods types ChatGPT said. Surface plasmon resonance (SPR) is an optical technique that measures molecular interactions in real time without the need for labels. It detects changes in the refractive index near a sensor surface, providing insights into binding kinetics and affinity. Several SPR methods have been developed, each with unique configurations and applications. 1. Traditional SPR configurations. Kretschmann configuration. This widely used setup involves a metal film, typically gold or silver, deposited on a glass prism. P-polarized light passes through the prism and reflects off the metal film. At a specific angle, resonance occurs, leading to a detectable drop in reflected light intensity. This configuration is favored for its simplicity and effectiveness in various analytical applications. Auto configuration. In this arrangement, a thin air gap separates the prism and the metal film. Light reflects internally within the prism, and the evanescent wave excites surface plasmons on the metal surface. While less common due to alignment challenges, the auto configuration is valuable for studying interactions at interfaces where direct contact with the metal is undesirable. 2. SPR imaging (SPRI). SPR imaging extends traditional SPR by enabling the simultaneous observation of multiple interactions across a sensor surface. It captures spatial variations in refractive index changes, allowing for high-throughput analysis. SPRI is particularly useful in applications like biomolecular interaction mapping and multiplexed assays. 3. Localized surface plasmon resonance (LSPR). LSPR focuses on the resonant oscillation of conduction electrons in metallic nanoparticles upon light exposure. The resonance condition is sensitive to the local dielectric environment, making LSPR a powerful tool for detecting molecular binding events at the nanoscale. Its high sensitivity and compatibility with various sample types make LSPR advantageous in biosensing applications. 4. Fiber optic SPR. This method integrates SPR sensors onto optical fibers, facilitating remote and in situ measurements. Light transmitted through the fiber interacts with the sensor surface, and changes in the refractive index are monitored. Fiber optic SPR is beneficial for applications requiring flexible sensor placement, such as environmental monitoring and in vivo studies. 5. Graphene enhanced SPR. Incorporating graphene layers onto SPR sensors enhances their performance due to graphene's exceptional electrical and mechanical properties. Graphene increases the sensitivity of SPR sensors and provides a biocompatible surface for biomolecule immobilization. This enhancement is particularly useful in detecting low abundance analytes and improving sensor robustness. Sample question and solution. Question. Describe the Kretschmann configuration in surface plasmon resonance and explain how it facilitates the excitation of surface plasmons. Answer. In the Kretschmann configuration, a thin metal film is deposited on the base of a glass prism. P-polarized light is directed through the prism and reflects off the metal film. At a specific incident angle, known as the resonance angle, the momentum of the incident photons matches that of the surface plasmons, leading to their excitation. This resonance results in a minimum in the reflected light intensity, which can be detected and analyzed to study molecular interactions occurring at the sensor surface. Multiple choice questions. Which SPR configuration involves a metal film directly deposited on a glass prism, allowing P-polarized light to excite surface plasmons at a specific angle? A. Auto configuration. B. Kretschmann configuration. C. Fiber optic SPR. D. Localized surface plasmon resonance. Answer. B. Kretschmann configuration. Which SPR method enhances sensor performance by incorporating a material known for its exceptional electrical properties? A. SPR imaging. B. Localized surface plasmon resonance. C. Graphene enhanced SPR. D. Fiber optic SPR. Answer. C. Graphene enhanced SPR. What is the primary advantage of fiber optic SPR sensors? A. High throughput analysis. B. Remote and in situ measurements. C. Nanoscale sensitivity. D. Enhanced electrical conductivity. Answer. B. Remote and in situ measurements. Understanding the various SPR methods and their configurations is essential for selecting the appropriate technique tailored to specific analytical requirements, thereby optimizing the sensitivity and accuracy of molecular interaction studies. Sources. You said. Relative lowering of vapor pressure. ChatGPT said. Relative lowering of vapor pressure introduction. Relative lowering of vapor pressure is a colligative property of solutions, meaning it depends only on the number of solute particles in a solution, not their identity. It is one of the fundamental principles of solution chemistry and is used to determine molecular weights of solutes. Definition. When a non-volatile solute is added to a pure solvent, the vapor pressure of a solution is lower than that of the pure solvent. The extent of this decrease is proportional to the concentration of the solute. The relative lowering of vapor pressure is defined as PO minus PPO equals N2N1 plus N2 approximately equals N2N1. For dilute solutions, P0. PO minus P equals N1 plus N2. N2. Approximately equals N1. N2. For dilute solutions where PO P0 equals vapor pressure of the pure solvent P. P equals vapor pressure of the solution N. 1 N1 equals number of moles of solvent N. 2 N2 equals number of moles of solute for very dilute solutions N. 2 N2 is much smaller than N. 1 N1. So the equation simplifies to PO minus PPO equals N2 N1 P0. PO minus P equals N1. N2. This equation shows that the relative lowering of vapor pressure is directly proportional to the mole fraction of the solute. Raoult's law and explanation. The concept of relative lowering of vapor pressure is derived from Raoult's law, which states P equals PO dot operator X1 P equals PO dot operator X1. Where X1 is the mole fraction of a solvent in the solution. Since the mole fraction of a solvent decreases with the addition of solute, the vapor pressure of a solution is always lower than that of the pure solvent. Molecular weight determination. The relative lowering of vapor pressure can be used to determine the molecular weight of a solute. From the formula PO minus PPO equals W2 dot operator M1 W1 dot operator M2 P0. PO minus P equals W1 dot operator M2. W2 dot operator M1. Where W1 W1 and W2 W2 are the masses of the solvent and solute, respectively. M1 M1 and M2 M2 are the respective molecular weights. Rearranging the equation to solve for M2 M2. M2 equals W2 dot operator M1 W1 dot operator PO PO minus PM2 equals W1. W2 dot operator M1. Dot operator PO minus PP0. This method is particularly useful for determining the molar mass of large biomolecules and polymers. Factors affecting vapor pressure lowering. Nature of the solute and solvent. Non-volatile solutes lower vapor pressure significantly, while volatile solutes may contribute to the vapor phase. Concentration of solute. Higher solute concentration results in greater vapor pressure lowering. Temperature. At higher temperatures, vapor pressures are higher, but the relative lowering remains the same. Applications. Determination of molecular weights of solutes. Used in osmotic pressure and colligative property studies. Helps understand the working of antifreeze solutions in vehicles. Used in designing solutions for pharmaceutical and industrial applications. Solved question from previous years. Question. The vapor pressure of a pure solvent is 600 mm of mercury, and that of a solution containing 10 grams of a solute in 180 grams of solvent is found to be 580 mm of mercury. Calculate the molecular weight of the solute. Solution. Given. PO equals 600 P0. Equals 600 mm of mercury P. Equals 580. P equals 580 mm of mercury W. 1 equals 180 W1. Equals 180 grams W. 2 equals 10 W2. Equals 10 grams M. 1 equals 18 M1. Equals 18 grams per mole assuming solvent is water using the formula PO minus PPO equals W2 dot operator M1 W1 dot operator M2 P0. PO minus P equals W1 dot operator M2. W2 dot operator M1. 600 minus 580,600 equals 10 times 18,180 times m2,600,600 minus. Thus, the molecular weight of the solute is 30 grams per mole. Multiple choice questions, MCQs. What is the relative lowering of vapor pressure a direct consequence of? A. Decrease in boiling point. B. Increase in osmotic pressure. C. Addition of a non-volatile solute. D. Increase in solute vapor pressure. Answer. C. Addition of a non-volatile solute. Which colligative property is directly related to Raoult's law? A. Osmotic pressure. B. Elevation of boiling point. C. Relative lowering of vapor pressure. D. Depression in freezing point. Answer. C. Relative lowering of vapor pressure. If the vapor pressure of a solution is 80% of that of the pure solvent, what is the mole fraction of the solvent in a solution? A. 0.8. B. 0.2. C. 1.2. D. 0.5. Answer. A. 0.8. This concludes the complete and detailed study material on relative lowering of vapor pressure for your PhD entrance exam in zoology. You said. Elevation of boiling point. ChatGPT said. Elevation of boiling point introduction. Elevation of boiling point is a colligative property of solutions, meaning it depends only on the number of solute particles in the solution and not on their identity. When a non-volatile solute is added to a pure solvent, the boiling point of a solution increases compared to that of the pure solvent. This phenomenon is known as boiling point elevation. Definition. The elevation of boiling point delta TB delta TB is the difference between the boiling point of the solution T BTB and the boiling point of the pure solvent T B0 TB0. Delta TB equals TB minus TB0. Delta TB equals TB minus TB0. Where TB0 TB0 equals boiling point of pure solvent T BTB equals boiling point of the solution. Raoult's law and explanation. When a non-volatile solute is dissolved in a solvent, the vapor pressure of the solution decreases. Since the boiling point is the temperature at which the vapor pressure equals the atmospheric pressure, a lower vapor pressure means that a higher temperature is required for the solution to boil. This results in an elevation of the boiling point. The elevation in boiling point is given by the ebullioscopic equation. Delta TB equals KB dot operator M. Delta TB equals KB dot operator M, where delta TB equals boiling point elevation K BKB equals ebullioscopic constant, boiling point elevation constant, of the solvent M. M equals molality of the solute, moles of solute per kilogram of solvent, molecular weight determination. Boiling point elevation can be used to determine the molecular weight of an unknown solute using the formula M2 equals KB dot operator. Values affecting the degree of boiling point elevation. Concentration of solute. More solute particles result in a greater elevation of boiling point. Ionization of solute. Electrolytes dissociate into multiple particles, leading to a higher boiling point elevation compared to non-electrolytes. Atmospheric pressure. Boiling points vary with external pressure, but the elevation principle remains the same. Applications. Antifreeze in vehicles. Ethylene glycol is added to water in radiators to increase the boiling point, preventing overheating. Cooking at high altitudes. Adding salt to water increases the boiling point, allowing food to cook at a higher temperature. Molecular weight determination. Used in research and industry to find unknown solute molar masses. Pharmaceutical industry. Helps in drug formulation by controlling solution properties. Solved previous year question. Question. A solution containing 0.5 grams of a solute in 100 grams of water elevates the boiling point by 0.13 degrees Celsius. The ebullioscopic constant K for water is 0.52 K kilogram per mole. Find the molecular weight of the solute. Solution, given. Delta TB equals 0.13 degrees. C delta TB equals 0.13 degrees Celsius K. B equals 0.52 K. B equals 0.52 K kilogram per mole W. 2 equals 0.5 W2 equals 0.5 grams W. 1 equals 100 W1 equals 100 grams equals 0.1 kilograms using the formula. M2 equals KB dot operator W2 delta TB dot operator W1 M2 equals delta TB dot operator W1 KB dot operator W2 M2 equals 0.52 times A. Increase in vapor pressure. B. Decrease in vapor pressure. C. Increase in solute mass. D. Decrease in atmospheric pressure. Questions. MCQs. What is the main reason for the elevation of boiling point in a solution? A. Increase in vapor pressure. B. Decrease in vapor pressure. C. Increase in solute mass. D. Decrease in atmospheric pressure. Answer. B. Decrease in vapor pressure. Which of the following is the correct relation for boiling point elevation? A. Delta TB equals KB dot operator M. Delta TB equals KB dot operator M. B. Delta TB equals KB per meter. Delta TB equals KB per meter. C. Delta TB equals KB dot operator M2. Delta TB equals KB dot operator M2. D. Delta TB equals KB dot operator W2 W1. Delta TB equals KB dot operator W2 W1. Answer. A. Delta TB equals KB dot operator M. Delta TB equals KB dot operator M. Which of the following solvents has the highest ebullioscopic constant K? B. KB. A. Water. B. Benzene. C. Chloroform. D. Carbon tetrachloride. Answer. A. Water. This concludes the detailed study material on elevation of boiling point for your PhD entrance exam in zoology. You said. Depression of freezing point. ChatGPT said. Depression of freezing point introduction. Depression of freezing point is a colligative property of solutions, meaning it depends only on the number of solute particles in the solution and not on their identity. When a non-volatile solute is added to a pure solvent, the freezing point of a solution is lower than that of the pure solvent. This phenomenon is known as freezing point depression. Definition. The freezing point depression delta TF delta TF is the difference between the freezing point of the pure solvent T F0 TF0 and the freezing point of the solution T FTF. Delta TF equals TF0 minus TF delta TF equals TF0 minus TF, where TF0 TF0 equals freezing point of the pure solvent T FTF equals freezing point of the solution. Raoult's law and explanation. The freezing point of a substance is the temperature at which its solid and liquid phases are in equilibrium. When a non-volatile solute is added to a solvent, the vapor pressure of the solvent decreases, meaning the liquid phase remains stable at lower temperatures, thus requiring a lower temperature for freezing to occur. This results in freezing point depression. The freezing point depression is mathematically given by delta TF equals KF dot operator M delta TF equals KF dot operator M, where delta TF equals freezing point depression K FKF equals cryoscopic constant, freezing point depression constant, of the solvent M. M equals molality of the solute, moles of solute per kilogram of solvent, molecular weight determination. The freezing point depression can be used to determine the molecular weight of an unknown solute using the formula M2 equals KF dot operator W2 delta TF dot operator W1 M2 equals delta TF dot operator W1 KF dot operator W2, where M2 equals molecular weight of the solute W 2 W2 equal mass of the solute G W 1 W1 equals mass of the solvent kilogram K FKF equals cryoscopic constant delta TF delta TF equals freezing point depression factors affecting freezing point depression. Nature of the solvent. Different solvents have different K FKF values affecting the degree of freezing point depression. Concentration of solute. A higher solute concentration results in greater freezing point depression. Ionization of solute. Electrolytes dissociate into multiple particles, leading to a higher freezing point depression compared to non-electrolytes. Atmospheric pressure. External pressure has little effect on freezing point depression, unlike boiling point elevation. Applications. Antifreeze in vehicles. Ethylene glycol is added to radiator water to lower the freezing point, preventing engine freezing in cold climates. Salt spreading on roads. Salt NaCl is spread on icy roads in winter to lower the freezing point of water, preventing ice formation. Preservation of biological samples. Freezing point depression is used in cryopreservation techniques. Food industry. Used in ice cream preparation to control freezing properties. Solved previous year question. Question. A solution contains 1.5 grams of a solute in 100 grams of water and lowers the freezing point by 0.279 degrees Celsius. The cryoscopic constant K FKF for water is 1.86 K kilogram per mole. Calculate the molecular weight of the solute. Solution given. Delta TF equals 0.279 degrees. C delta TF equals 0.279 degrees Celsius. K F equals 1.86 K. F equals 1.86 K kilogram per mole. W 2 equals 1.5 W2 equals 1.5 grams. W 1 equals 100 W1 equals 100 grams equals 0.1 kilograms using the formula 2 equals KF dot operator W2 delta TF dot operator W1 M2 equals delta TF dot operator W1 KF dot operator W2 M2 equals 1.86 times 1.50 0.279 times 0.1 M2 equals 0.279 times 0.1 1.86 times 1.5 M2 equals 2.79 0.0279 equals 100 grams per mole. M 2 equals 0.0279 2.79 equals 100 grams per mole. Thus, the molecular weight of the solute is 100 grams per mole. Multiple choice questions. MCQs. Why does the freezing point of a solution decrease when a solute is added? A. Solute increases the kinetic energy of solvent molecules. B. Solute interferes with the formation of the solid phase. C. The density of the solution increases. D. The solution becomes less volatile. Answer. B. Solute interferes with the formation of the solid phase. Which equation represents freezing point depression? A. Delta TF equals KF dot operator M delta TF equals KF dot operator MB delta TF equals KF per meter delta TF equals KF per meter. C. Delta TF equals KF dot operator M2 delta TF equals KF dot operator M2. D. Delta TF equals KF dot operator W2 W1 delta TF equals KF dot operator W2 W1. Answer. A. Delta TF equals KF dot operator M delta TF equals KF dot operator M. Which of the following substances is commonly used as an antifreeze agent? A. Acetone. B. Ethylene glycol. C. Benzene. D. Chloroform. Answer. B. Ethylene glycol. This concludes the detailed study material on freezing point depression for your PhD entrance exam in zoology. You said, osmotic pressure. ChatGPT said, osmotic pressure introduction. Osmotic pressure is a fundamental colligative property of solutions that plays a crucial role in biological systems, particularly in cell physiology and homeostasis. It is the pressure required to stop the movement of solvent molecules across a semi-permeable membrane from a region of lower solute concentration to a region of higher solute concentration. This movement of solvent is called osmosis. Definition: osmotic pressure pi. Pi is defined as the minimum pressure that must be applied to a solution to prevent the net flow of solvent molecules across a semi-permeable membrane. Mathematically, it is given by the Van Hoff equation. Pi equals ICRT. Pi equals ICRT where pi equals osmotic pressure in atm. I equals Van Hoff factor accounts for ionization of solute. C equals molar concentration of the solute mole per liter. R equals universal gas constant 0.0821 LATM mole minus 1 minus 1 K minus 1 minus 1 T. T equals absolute temperature in Kelvin if the solution contains non-electrolytes. I equals 1. I equals 1. For electrolytes, I depends on the degree of dissociation of the solute. Mechanism of osmosis. Osmosis occurs when a semipermeable membrane separates two solutions of different solute concentrations. The solvent moves from the region of lower solute concentration, higher solvent potential, to the region of higher solute concentration, lower solvent potential until equilibrium is reached. Types of solutions based on osmotic pressure. Isotonic solution, a solution with the same osmotic pressure as the cytoplasm of a cell, causing no net water movement across the membrane. Hypotonic solution, a solution with lower osmotic pressure than the cell cytoplasm, causing water to enter the cell, leading to swelling or bursting lysis. Hypertonic solution, a solution with higher osmotic pressure than the cell cytoplasm, causing water to leave the cell, leading to shrinking prenation in animal cells or plasmolysis in plant cells. Applications of osmotic pressure. 1. Biological importance. Cell membrane transport, regulates water movement in and out of cells. Blood plasma and IV fluids. IV fluids must be isotonic to prevent red blood cells from shrinking or swelling. Plant water regulation, plants absorb water from the soil through root osmosis. 2. Industrial applications. Food preservation, high sugar or high salt solutions create a hypertonic environment that prevents bacterial growth. Reverse osmosis RO, water purification, uses high pressure to force water through a membrane, removing contaminants. 3. Determination of molar mass. Osmotic pressure can be used to determine the molar mass of unknown macromolecules, such as proteins and polymers, using the formula M2 equals W2RT pi V M2 equals pi V W2RT. Where M2 equals molecular weight of the solute W. 2W2 equals mass of the solute G P. V equals volume of a solution L pi. Pi equals osmotic pressure ATM R. R equals gas constant 0.0821 L ATM mole minus 1 minus 1 K minus 1 minus 1 T. T equals temperature K. Solve previous year question. A 0.1 m solution of a non-electrolyte in water at 27 degrees Celsius, 300 K exerts an osmotic pressure of 2.46 atmospheres. Calculate the molecular weight of the solute. Solution, given. Pi equals 2.46. Pi equals 2.46 atmospheres C. Equals 0.1. C equals 0.1 moles per liter R. Equals 0.0821. R equals 0.0821 L ATM mole minus 1 minus 1 K minus 1 minus 1. T equals 300 T equals 300 K. Using Van Hoff's equation. Pi equals CRT 2.46 equals 0.1 times 0.0821 times 300. 2.46 equals 0.1 times 0.0821 times 300. 2.46 equals 2.463. 2.46 equals 2.463. Since both sides are nearly equal, the calculation is verified. Now, to find molecular weight M. 2M2. Use M2 equals W2RT pi V M2 equals pi V W2RT. If a solution contained 1 gram of solute in 1 L, we get M2 equals 1 times 0.0821 times 300. 2.46 M. 2 equals 2.46. 1 times 0.0821 times 300. M2 equals 24.63. 2.46 equals 100 grams per mole M. 2 equals 2.46. 24.63 equals 100 grams per mole. Thus, the molecular weight of the solute is 100 grams per mole. Multiple choice questions MCQs. What is osmotic pressure? A. The pressure required to stop the movement of solute molecules. B. The pressure required to stop the movement of solvent molecules. C. The pressure needed to break the semipermeable membrane. D. The pressure exerted by a solution on its surroundings. Answer. B. The pressure required to stop the movement of solvent molecules. Which of the following is not an application of osmotic pressure? A. Reverse osmosis water purification. B. Determination of molecular weight. C. Increasing vapor pressure of a solvent. D. Regulating water balance in cells. Answer. C. Increasing vapor pressure of a solvent. Which equation represents osmotic pressure correctly? A. Pi equals ICRT. Pi equals ICRTB. Pi equals KFM. Pi equals KFMC. Pi equals KBM. Pi equals KBMD. Pi equals CRTI. Pi equals CRTI. Answer. A pi equals ICRT. Pi equals ICRT. This concludes the detailed study material on osmotic pressure for your PhD entrance exam in zoology. You said, Fick's law and diffusion coefficient. ChatGPT said, Fick's law and diffusion coefficient introduction. Diffusion is the process by which molecules move from an area of higher concentration to an area of lower concentration due to random molecular motion. This process is essential in various biological and physical systems, including gas exchange in lungs, nutrient transport in cells, and the movement of ions across membranes. Fick's laws describe the fundamental principles governing diffusion. These laws are widely used in biology, chemistry, and physics to understand and quantify the movement of molecules in different media. Fick's first law of diffusion. Fick's first law states that the rate of diffusion is directly proportional to the concentration gradient. Mathematically, it is expressed as J equals minus d dc dx. J equals minus d dx dc. Where J equals diffusion flux, amount of substance per unit area per unit time, mole M minus 2s minus 1 minus 1 d. D equals diffusion coefficient M2. 2 S dc dx. dc dx equals concentration gradient, change in concentration per unit distance. The negative sign indicates that diffusion occurs from higher to lower concentration. Biological significance. Oxygen diffusion in cells. Oxygen moves from capillaries, high concentration, into tissues, low concentration. Lung gas exchange. Oxygen diffuses from alveoli into the blood, while CO moves in the opposite direction. Passive transport across membranes. Small molecules like CO and O diffuse across cell membranes following their concentration gradients. Fick's second law of diffusion. Fick's second law describes how concentration changes with time. It is expressed as Partial differential C partial differential T equals D partial differential 2 C partial differential X2 partial differential T partial differential C equals D partial differential X2. Partial differential 2C. Where? Partial differential C partial differential T partial differential T partial differential C equals change in concentration with time partial differential. 2C partial differential X2 partial differential X2. Partial differential 2C equals second derivative of concentration with respect to position D. D equals diffusion coefficient. Implications of Fick's second law predicts how solutes spread over time in a medium. Used in drug delivery to model the release of medication from a tablet into the bloodstream. Helps explain pollutant dispersion in the environment. Diffusion coefficient. D. The diffusion coefficient, also called the diffusivity, is a measure of how fast a substance diffuses in a medium. It is influenced by nature of the diffusing substance. Smaller molecules diffuse faster than larger ones. Nature of the medium. Diffusion is faster in gases than in liquids and solids. Temperature. Higher temperatures increase diffusion rates due to greater molecular motion. Viscosity of the medium. Higher viscosity slows diffusion. The diffusion coefficient is determined using Stokes-Einstein equation for diffusion in liquids. D equals kBT 6 pi eta RD equals 6 pi RK. BT. Where? KB equals Boltzmann constant 1.38 times 10 minus 23 minus 23 J KT. T equals temperature K eta. Eta equals viscosity of the medium Pa S R. R equals radius of the diffusing molecule M. Applications of Fick's laws 1. Biological applications. Gas exchange in lungs. The rate of oxygen and carbon dioxide exchange follows Fick's first law. Nutrient absorption. Glucose and amino acids diffuse into cells based on concentration gradients. Neuronal signaling. Neurotransmitters diffuse across synaptic clefts. 2. Industrial applications. Drug delivery systems, used to design controlled release medications. Food industry, diffusion is key in marination and flavor infusion. Membrane filtration, used in dialysis and water purification. 3. Environmental applications. Pollution control, understanding how pollutants spread in air and water. Soil chemistry, movement of nutrients and pesticides in soil follows diffusion principles. Solved previous year question. Question. The diffusion coefficient of oxygen in water at 25 degrees Celsius is 2.5 times 10 minus 9 minus 9 meters 22. S. If the oxygen concentration changes from 8 mg per liter to 2 mg per liter over a distance of 1 millimeter, what is the diffusion flux according to Fick's first law? Solution, given. D equals 2.5 times 10 minus 9. D equals 2.5 times 10 minus 9. M22 per second C1 equals 8 C1. Equals 8 mg per liter, C. 2 equals 2 C2. Equals 2 mg per liter distance, X. Equals 1. X equals 1 millimeter equals 1. Times 10 minus 3. 1 times 10 minus 3 meters. Using Fick's first law. J equals minus d dc dx. J equals minus d dx dc. J equals minus 2.5 times 10 minus 9 times 2 minus 8, 1 times 10 minus 3. J equals minus 2.5 times 10 minus 9 times 1 times 10 minus 3. 2 minus 8. J equals minus 2.5 times 10 minus 9 times minus 6 times 10 3. J equals minus 2.5 times 10 minus 9 times minus 6 times 10 3. J equals 1.5 times 10 minus 5. Mole per meter 2. S. J equals 1.5 times 10 minus 5. Mole per meter 2. S. Thus, the diffusion flux is 1.5 times 10 minus 5 minus 5 mole square meter per second. Multiple choice questions MCQs. According to Fick's first law, the rate of diffusion depends on the concentration gradient. B. The viscosity of the medium. C. The volume of the solution. D. The surface area of the membrane. Answer. The concentration gradient. Which of the following does not affect the diffusion coefficient? A. Temperature. B. Molecular weight of the substance. C. Concentration gradient. D. Viscosity of the medium. Answer. C. Concentration gradient. Which equation represents Fick's first law? A. J equals minus d dc dx. J equals minus d dx dc. B. J equals partial differential C partial differential T. J equals partial differential T partial differential C. C. J equals CRT. J equals CRT. D. J equals kBT 6 pi eta R. J equals 6 pi RK. BT. Answer. A. J equals minus d dc dx. J equals minus d dx dc. This concludes the detailed study material on Fick's law and diffusion coefficient for your PhD entrance exam in zoology. You said. Stokes-Einstein's law. ChatGPT said. Stokes-Einstein law introduction. The Stokes-Einstein law describes the relationship between the diffusion coefficient of a particle in a fluid and its size, temperature, and viscosity of the medium. This law is fundamental in understanding the diffusion of macromolecules, nanoparticles, and biological molecules in different media. It is widely applied in biophysics, chemistry, and microbiology to study molecular motion in solutions. Stokes-Einstein equation. The Stokes-Einstein equation is given by D equals kBT 6 pi eta RD equals 6 pi RK. BT. Where? D equals diffusion coefficient M2. 2. S KB equals Boltzmann constant 1.38 times 10 minus 23 minus 23 J KT. T equals absolute temperature Kelvin eta. Eta equals viscosity of the medium Pa S R. R equals radius of the particle M. This equation shows that smaller particles diffuse faster and higher temperatures increase diffusion. Conversely, a higher viscosity slows diffusion. Derivation and explanation. The Stokes-Einstein equation combines two principles. Stokes' law describes the drag force F. dFd. Acting on a sphere moving through a fluid. Fd equals 6 pi eta R versus Fd. Equals 6 pi RV where V is the velocity of the particle. Einstein's relationship relates diffusion to Brownian motion. D equals kBT gamma. D equals gamma kBT. where gamma. Gamma is the friction coefficient, which is given by 6 pi eta r. 6 pi r from Stokes' law. By substituting gamma equals 6 pi eta r. Gamma equals 6 pi r into Einstein's equation, we get the Stokes-Einstein equation. Significance of Stokes-Einstein law: smaller molecules move faster than larger ones in a given medium. Higher temperatures increase molecular diffusion. More viscous fluids slow down molecular movement. Used to estimate the size of molecules and particles in solutions. Applications of Stokes-Einstein law 1. Biological applications. Protein and DNA diffusion helps in understanding how biomolecules move in cytoplasm and membranes. Cellular transport, used to study vesicle transport within cells. Drug delivery systems, predicts the movement of nanoparticles in body fluids. 2. Industrial and chemical applications. Nanoparticle research, determines how nanoparticles diffuse in colloidal suspensions. Quality control in pharmaceuticals, used in particle size analysis of drug formulations. Viscosity measurements, helps determine viscosity of unknown fluids using diffusion data. 3. Environmental and engineering applications. Oil and water separation, helps in designing efficient separation techniques. Pollution studies, predicts the spread of contaminants in water bodies. Solved previous year question. Question. A protein molecule of radius 2 nanometers is diffusing in water at 25 degrees Celsius, 298 K. The viscosity of water is 0.89 times 10 minus 3 minus 3. Pa s. Calculate its diffusion coefficient. Solution, given. R equals 2 times 10 minus 9. R equals 2 times 10 minus 9. MT equals 298, T equals 298 K eta. Equals 0.89 times 10 minus 3. Eta equals 0.89 times 10 minus 3. Pa s K. B equals 1.38 times 10 minus 23 KB. Equals 1.38 times 10 minus 23. J, K. Using the Stokes-Einstein equation. D equals KBT 6 pi eta R. D equals 6 pi RK. BT. D equals 1.38 times 10 minus 23, 298, 6 pi. 0.89 times 10 minus 3, 2 times 10 minus 9. D equals 6 pi. 0.89 times 10 minus 3. 2 times 10 minus 9. 1.38 times 10 minus 23. 298. D equals 4.11 times 10 minus 21, 3.36 times 10 minus 11. D equals 3.36 times 10 minus 11. 4.11 times 10 minus 21. D equals 1.22 times 10 minus 10 meters 2 per second. D equals 1.22 times 10 minus 10 m2 per second. Thus, the diffusion coefficient of the protein is 1.22 times 10 minus 10 square meters per second. Multiple choice questions, MCQs. According to the Stokes-Einstein equation, the diffusion coefficient D is inversely proportional to a temperature. B particle radius C, Boltzmann constant D, none of the above. Answer, B particle radius. Which of the following factors will increase the diffusion coefficient? A. Increasing the viscosity of the medium. B. Increasing the temperature. C. Increasing the particle size. D. All of the above. Answer, B. Increasing the temperature. The Stokes-Einstein equation applies to A. Only gaseous diffusion. B. Only liquid diffusion. C. Diffusion of spherical particles in a fluid. D. Solid state diffusion. Answer, C. Diffusion of spherical particles in a fluid. This concludes the detailed study material on Stokes-Einstein law for your PhD entrance exam in zoology. You said. Gibbs done an equilibrium. ChatGPT said. Gibbs done an equilibrium. Introduction. Gibbs done an equilibrium or done an equilibrium describes the distribution of charged ions between two solutions separated by a semi-permeable membrane, where one side contains an impermeable charged species, such as a protein or macromolecule. This concept is fundamental in cell biology, physiology, and biophysics, especially in understanding ion transport across cell membranes, osmotic balance, and electrochemical gradients. Concept of Gibbs done an equilibrium. When two solutions are separated by a membrane that allows small ions to pass but restricts large, charged molecules, e.g., proteins or macromolecules, an unequal distribution of diffusible ions occurs. This leads to electrochemical imbalance. The movement of small ions generates an electric potential. Osmotic effects. Water moves to balance the osmotic pressure, affecting cell volume. Ion concentration differences. The impermeable ions cause an asymmetric distribution of permeable ions. This phenomenon plays a crucial role in nerve signaling, kidney function, and intracellular fluid balance. Mathematical representation. If an impermeable negatively charged macromolecule, such as a protein, is present in one compartment, it attracts cations and repels anions. The Donen equilibrium is mathematically expressed as C1 plus times C1 minus equals C2 plus times C2 minus C1 plus times C1 minus equals C2 plus times C2 minus, where C1 plus and C1 minus equals concentrations of cations and anions on one side of the membrane. C2 plus C2 plus and C2 minus equals concentrations of cations and anions on the other side. This equation states that the product of ion concentrations on each side remains equal at equilibrium. Donen potential E. DED. The electrical potential difference E. DED. Created across the membrane due to ion imbalance is given by the Nernst equation. ED equals RTZF lane C1 plus C2 plus ED equals ZFRT. Lane C2 plus C1 plus. Where R equals universal gas constant 8.314 J per mole KT. T equals absolute temperature KC. C equals charge of the ion F. F equals Faraday's constant 96,485 C per mole C. 1 plus C1 plus and C2 plus C2 plus. equals cation concentrations on both sides. Biological significance 1. Cell membrane and ion balance. The Dunning effect influences ion distribution across cell membranes, especially in neurons and red blood cells. Cells maintain ion